Yesterday we introduced the third of three of Newton's laws. That was called Newton's third law. It says, well, at least it said back in grade 6, it said for every action there's an equal and opposite reaction. We like to state it a little bit differently now. Okay, we like to state it as if object A applies a force on object B, then object B applies an equal and opposite force on object A. So if object B hits object A and vice versa, then there's going to be a force on object A due to B, but there's also going to be an equal and opposite force on object B due to A. Are these always going to be equal and opposite? Every single time, no exceptions. We did a couple examples yesterday of when it might not seem like it is equal. Okay, let's say that you're a boxer, okay, and you punch somebody in the face with your boxing glove on. Is there equal and opposite forces there? Absolutely. It might hurt the guy's face more than it hurts your hand, but in the end, his hand is still applying an equal and opposite force back on your hand than his face. Okay? You kick the end of the bed. Okay? When you're getting up in the middle of the night, you kick the end of the bed. Okay? You apply a force of 100 newtons on the bedpost. What does the bed do? It applies a force of 100 newtons back on your toe. Okay? You throw a rock at the window breaks. The rock applied a force of 600 newtons in order to break the window. What force did the window apply back on the rock? 600 newtons. Why did the window break but not the rock? The window can't hold 600 newtons, right? The rock can. The rock is stronger than the window. Here's one for you. A smart car is involved in a head-on collision with a semi-truck. Now, that's not good. Okay, you don't want to see that. A smart car is involved in a head-on collision with a semi-truck. Two different vehicles, dramatically different vehicles, right? Which one applies the bigger force? The smart car or the semi-truck? They're the same. If object A applies a force on object B applies an equal and opposite force on object A. So why is the smart car more heavily damaged than the semi-truck? Better yet, why does a smart car, when it hits a semi-truck, just go flying backwards, basically? And the semi-truck pretty much just bowl right through it. Yep. Because the semi-truck weighs more? Yes. Could you be more specific? Could you say a little bit more there, Jazzy? Okay. So the smart car might be destroyed because it can't take as much force as a semi-truck can hold. Why does it go backwards? Why does the semi-truck keep going forwards and the smart car go backwards? And Kevin alluded to this when he said mass, right? Okay, the smart car weighs less than the semi-truck. Okay, if the smart car weighs less and we apply the same force on it, it's going to... Yeah, it does. It does because it has more mass, yeah. If the smart car weighs less and we apply a force of, let's say, 10,000 newtons on the smart car, it will accelerate at a really, really high rate. If the semi-truck weighs a lot and we apply the same force, it will accelerate at a lower rate, a smaller rate. So the one that has more mass will accelerate slower or decelerate slower, as the case may be, but it's still the same force. That make sense? If object A applies a force on object B always, every single time, applies an equal and opposite force on object A. Okay, no exceptions to that. Even when it seems like that rule might be broken, there's no exceptions to that. Okay? We're going to do some problems here, but they're kind of Newton's third law-ish, but kind of what we have been doing. We're just going to combine a couple little concepts here right now, okay? This first problem, and we see three boxes, A, B, and C. They're positioned next to each other. An applied force on box A causes all of the boxes to accelerate at 1.5. We want to find the force, and this is the tricky part of this one. We want to find the force exerted by box C on box B. In other words, what's the force in between them? I call that an internal force. An internal force versus an external force. When we apply an external force, we're causing the whole thing to do something. When we apply an internal force, we're acting between two things inside. It's kind of like this. Hey, my uncle, in his years ago, used to drive a semi-truck, used to deliver ice cream for this ice cream company in Ontario. And I lived on the East Coast. Every once in a while, my uncle would make a run to the East Coast, a load of ice cream to the East Coast to a warehouse in Halifax. And I remember when it would always look forward to when he came out because we didn't see him all that often. But I also like to, sit in the semi-truck and honk the horn and whatever. He'd always spend one night at my grandfather's house. We'd go out and see him, and as I say, we'd sit in the semi-truck as little kids. That was fun, right? And I remember this one time. The load of ice cream in the back of the semi-truck, or at least some of the pallets, one or two of the pallets in the back of the semi-truck, one or two of the pallets that are, filled with boxes of ice cream, tipped over or something happened to it. I can't remember exactly what it was. So some of the ice cream was dented. So some of the ice cream packages were dented. And I remember my uncle phones the boss and says, in Ontario, and says, what do I do with this? He said, well, the boss says, well, you can't deliver it. You can't leave this at the warehouse because nobody wants to buy dented ice cream boxes. It's like, well, what do I do with it then? He said, just leave it there. This was heaven, right? You're a little kid, and your uncle is leaving a pallet of ice cream, literally a pallet of ice cream. It was literally heaven. Guys, when the semi-truck, there's forces that act on the outside of that semi-truck, right? There's the wheels against the road. That's what pushes the semi-truck forward. There's the brakes. That's what stops the semi-truck or slows down the semi-truck. But there's also internal forces. There's forces that act within the trailer of the semi-truck. There's a force that's supposed to keep the pallet together, right? Everything is kind of wrapped, kind of plastic wrapped, right, to keep the pallet together. Okay, those aren't acting on the semi-truck itself. That's not causing the semi-truck to move forward or to slow down, but it is acting on pieces within the semi-truck. Does that make sense? Those are internal forces. Okay, the forces that are keeping the ice cream containers together are internal forces. They're important, but they don't contribute whatsoever to the motion of the truck. The external forces, the force of friction, the force of the tires on the road that push the truck forward, those are external forces. They're what contribute to the motion here. Okay, we're trying to find an internal force here between B and C. We're trying to find the force between the ice cream pallets, basically. They don't contribute to the motion of these boxes, okay, but they're still there. Those internal forces are still there. So how do we solve this then? How do we find that internal force between B and C? Well, the first thing that we want to do here, the very first thing that we want to do here is analyze this as one object, as one system. Okay? This is my semi-truck trailer. Box A is a box of ice cream. Box B is a box of ice cream. And box C is a box of ice cream. Okay? Let's pretend right now it's one object, and that's the semi-trailer. Treat it as one. It has an acceleration of 1.5 meters per second to the right. It says there is an applied force, we'll call that FA, that's applied on object A, which of course pushes them all. Okay, we don't know what its value is. I don't think we do we? No. But we do know the acceleration is 1.5 meters per second squared. What I want you to do first is not only draw the free body diagram for the back of the semi-truck, the trailer, the whole thing, right, these three boxes combined, but I want you to analyze the three of those combined as well. There is only one, I was going to say there's only one force acting here. That's not true, is it? What else is acting? What else is acting that I forgot, actually? Gravity and? Right. But what happens to those two forces? They cancel each other out, right? So there's only one force that's acting that contributes to this. Okay, and then that force is going to be equal to FA, the applied force. The net force is M times A. What mass do I use here? 8, 10, or 5? Or something else entirely? If I'm analyzing the back of the semi-truck, then I should use the entire mass of the back of the semi-truck, right? Which includes the mass of each of the boxes of ice cream inside the semi-truck. So I'm going to use a mass of everything there. It's going to be 23 kilograms. The acceleration of this system is 1.5 meters per second squared to the right. And we can solve for FA. Look at that. 23 times 1.5 is going to give me 34.5 newtons. Is that my answer? Is that what I'm looking for here? No, it isn't. That's okay. Whenever you see a problem where you want to analyze, where you want to find a force, an internal force, what you got to do first is analyze the external. Okay, analyze the whole system first. Now, every once in a while, you're going to do that, and you're going to find that, oops, I did a little bit too much work. I didn't have to do it. But most times, you're going to have to do it. So just do it. Okay, just analyze the external first. Now what we want to do, after we've done the external, we want to analyze the internal. So now what I want to do is draw a free body diagram for one of those objects. If I'm trying to find the force between B and C, which object should I pick to draw? A, B, or C? You got a couple of choices here. One you shouldn't draw. I want to find the force between B and C. Ice cream box B, ice cream box C. Don't draw object A. Okay, object A doesn't matter here. Okay, let's draw B or C. I'm going to pick C because C is the one on the end, and I think that's going to make it a little bit easier. So now what I'm doing is looking inside the ice cream truck. Okay, I don't want to analyze the whole trailer. I want to analyze the forces acting only on that box of ice cream. So object C has a mass of 1.5 kilograms. What forces act on object C? Well, there's gravity and a normal force, but they cancel. Sorry, it's 5 kilograms. But those two forces are still there, and those two forces still cancel each other out. 5 kilograms. What other force pushes on ice cream box C? We're assuming there's no friction here, because they would have told me if there was friction. Does object B push on C? Sure it does. The force of B on C. There are no others. So now let's analyze object C only. The force of B on C is equal to, the net force, I should say, is equal to the force of B on C. The net force is M times A. What mass do I use? 8. What was the other one? 10? 8, 10, or 5, or some sort of combination of them. Okay, 10? Why would I use 10? Okay, so the box that's doing the pushing has a mass of 10. The box that's being pushed has a mass of 5. Want to change that answer? Yeah. No, you want to always use the mass that's being pushed. Okay, the mass that's being accelerated. Now, the second one is, object B is being accelerated as well, right? Because it's going with the truck. The whole thing is accelerating. But I'm analyzing object C. If I'm analyzing object C and studying the motion of object C, then let's use the mass of object C. Okay? That makes sense, Kevin? Okay. So let's use that mass of 5 kilograms this time. Don't use 23 anymore. That's what I used when I was analyzing the system. Now I'm using 5. Acceleration is 1.5. And FBC is equal to 7.5. Now, there's a couple of things that kind of strike me at this point. One is that I'm not looking for the force of B on C. I'm looking for the force of C on B. Should I have done it this way? Do I have to start again? If I just found the force of B on C to be 7.5, then can you tell me what the force of C on B is going to be equal to? 7.5 in the opposite direction, right, because it's equal and opposite. Okay, I'm not real concerned in these questions if you get the negative or the positive. Okay, that's not a big deal. If you get the magnitude of the force that we're looking for, that's the important thing. Okay, so if we find BC, that's okay, even though that's not technically what we're looking for, because it's the same value, same magnitude as the force of C on B, which is what I'm looking for. The answer is 7.5 newtons. Now, the other thing that strikes me here is that I didn't actually use that 34.5 anywhere, did I? I calculated it and then I didn't use it. That's okay. Okay, honestly, guys, when I started this question, I didn't know I wasn't going to use that. I didn't know I wasn't going to use that 34.5. It occurred to me about halfway through that, oh, wait, I didn't need to do that. But that's okay. The strategy that I want you to follow when you're trying to find an internal force is to always analyze the external first and then analyze the internal. Because 95% of the time, you're going to need to use the number that you get from analyzing the external and put it into when you're analyzing the internal. Does that make sense? Picture the ice cream truck. Can you see inside the ice cream truck? Can you see it? Do you see all the ice cream right now inside the ice cream truck? As you're walking into the ice cream truck, what kind of ice cream is on your right-hand side? If you can't see it right now, you're not visualizing it, right? What kind of ice cream is on the right-hand side there, Joe? Maple walnut. That's a different kind. Is that your favorite? Yeah, that's my dad's favorite kind too, maple walnut. Maple walnut ice cream on the right-hand side. There's drumsticks on the left-hand side. And then there's ice cream sandwiches straight ahead. Hey, picture what's going, like, seriously, guys, of course, when you're analyzing a problem, you don't need to picture it in that kind of detail, right? But I want you to, like, literally visualize the entire truck, okay, not being able to see inside. So it doesn't matter A, B, and C. Visualize the entire truck from the outside. Do that first. Then visualize the inside of the truck. Okay, then visualize the individual ice cream boxes A, B, and C on the inside of the truck. And pick one of them to analyze. Okay? I'm sorry? You're welcome. You're very welcome. All right, if we're good with this, then let's take a look at a couple questions here. Okay, we're looking at the example in 3.12. We want to find the force that B exerts on A, and then another example in 3.9. Example 3.9, practice problem 1 on page 153. We want to find the force. You know what? Actually, let's forget about this one right now. Let's focus on this one right here, okay? Okay, it goes back to this example. Okay, we want to find the force that box B exerts on A. So in other words, we want to find this force this time. Okay? I'm going to leave this page up here so that you can see this. Okay, just remember the question. We want to find the force between A and B, not the force between B and C. Okay? Give me a couple minutes to do that now, and then we'll go over it as a class. All right, let's take a look at it then, guys, okay? The question asked me to find the force between A and B. Remember what we got to do first. The first is to analyze the external forces. The semi-truck trailer. Forget about the ice cream inside right now. It's the whole trailer with everything inside. Okay, analyze the external. We've already done that, right? We've already done that. We've found the applied force here to be 34.5 newtons. Okay, now we want to analyze one of the objects inside the truck, the internal forces. But we're not going to analyze object C like we did in the last question. If we want to find the force between A and B, let's pick either object A or B. Which one's easier to pick? B? I'd say probably A, actually. B works, but A would work. A would be a little bit easier because B has A pushing on it and C pushing on it. A doesn't have B pushing on it. Sorry, A doesn't have C pushing on it. It only has one of the objects pushing on it. So I'm going to pick object A. But you know what? Terry, you should get the same answer. Did you do it with object B? Okay, you should get the same answer. We'll see in just a moment here, okay? If you did it right, you should get the same answer as I get doing it, picking object A. All right, so look up here. We've analyzed the external. We've got an applied force of 34.5 newtons acting on the system, directly on object A and indirectly on the entire system. Let's draw a picture of object A. Object A has a mass of 8 kilograms. We know that there is an applied force of 34.5 newtons acting on object A. It's acting on the system, but they're telling me that it's acting directly on box A. But we also know there's a force of B on A. Right? Well, think about it. If you apply a force on object A and A is in contact with B, then A has got to push on object B, right? Otherwise, B is not going to go forward. Well, if A pushes on B, then B pushes on A. So there's a force this way of object B on A. And this is what we're trying to find right there. So let's say F net is equal to the sum of the forces, FA plus FBA. We're going to say M times A is equal to FA plus FBA. Mass is 8 kilograms. We're not using the entire mass, right? Because we're only analyzing one object within the system. The acceleration was 1.5. If the whole thing accelerates at 1.5, then every ice cream box within it also accelerates at 1.5, including object A. Eight times 1.5 is 12.5. 12.5 minus 34.5 gives me 22.5. Negative 22.5. Tara, did you get positive 22.5? Okay. So I did it. So I did this, guys. I got negative 22.5. Tara analyzed object B. She found not the force of B on A, but rather the force of A on B, and she got positive 22.5. Is that right? Who has a better answer here? They're both the same answer, right? Object A applies a force on object B. Object B applies an equal and opposite force on object A. The answer is 22.5. Whether it's positive or negative doesn't really matter. We're going to round that to how many digits? 2 digits. So negative 23 newtons. What do we do first? The external, the entire system. What do we do after that? The internal. We picked an object. I picked object A. Tara picked object B. Both of those make perfect sense. It doesn't make sense to pick object C because C doesn't have the force between A and B acting on it, and that's what we're looking for there. Okay. Yeah. Yep. Good question. If you're trying to find the force just of B on A, why do you need to take into account the applied force? Because that affects how hard B pushes on A. That's why we have to take it into account. Okay. Let's say that you're up against a wall, some kind of movable wall type thing. Okay, and I push you. Okay, I push you with a force of 10 newtons. Not very hard. Okay. And as I push you, the wall starts moving as a result of that, right? I push on you, you push on the wall, okay, the wall starts moving, right? Make sense? Now, how hard you push on the wall is going to depend upon how hard I pushed on you. Does that make sense? So therefore, how hard the wall pushed back on you depends upon how hard I pushed on you. So why do we need to take into account FA here when we're only trying to find the force of B on A? Because the value of that depends upon how hard I pushed on object A. Yep. Yep. Okay, that's an even better question. Now Spencer's saying, well, okay, she's all good with this now, I think. But she's saying now, well, why when we analyzed object C did we not take into account the applied force then, right? Well, because if you look at individually, the individual forces, okay, object A is FA is pushing on object A. A pushes on B, B pushes on C. Okay? Force A doesn't apply a force directly on C. Now, if it wasn't there, there would be no force of B on C. The value of force B on C is dependent upon the force that we push on object A with. But that force doesn't act directly on C. When we're drawing a free body diagram for object C, we need to include all the forces that act on object C. Here, we included that because FA acts on object A directly. Okay, whereas in the other one it didn't. It was an indirect force. Okay. Let's try another one. Okay, as a group here, okay? The first thing that we got to do here, when we got a problem like this where we want to find the tension in the rope here. Okay, we want to find how hard object 1 is pulling on object 2 or object 2 is pulling on object number 1. The first thing we got to do is analyze the external. The whole thing. And then we analyze the internal. Here's the external, the whole thing. On this entire system, there is what acting? On the whole thing, what's acting on it? There's an applied force, right? It's acting on the whole thing. If you don't have that applied force, the system's not going to move. Okay, if this green box is the back of my semi-truck, and this 10-kilogram box and this 15-kilogram box are my boxes of ice cream, if I don't have that 50 newtons pulling it forward, then nothing's going to move. Whether you're talking about the truck or the ice cream inside, nothing's going to move. Okay, that force of 50 newtons is being applied on the entire system. Is there anything else that contributes or takes away from the motion of this system? If you have friction acting on individual things within it, does that take away from the motion of the system? If I got a row of 5 desks here right now, I'm not going to push all 5 of them because with the desks full of people, I'm not going to be able to push all 5 of them. Okay, but let's say that I was pushing on all 5 of them, okay? Pushing backwards on all 5 of them. I push with 50 newtons. That contributes to the motion of the system, right? The external, the whole thing. There's a force of friction of 5 newtons acting on each of these desks. Does that take away from the motion of the system? Sure it does. Sure it does. So these forces of friction, although they act individually on the 10 and the 15, they also take away from the motion of the system itself. So we've got 3 forces that act on the system, the external. FA, FF1, that's this one, and FF2, that's this one. Say M times A is equal to those 3 forces. M is 25 kilograms because I'm analyzing the whole system, external. FA is negative 20. FF1 was negative 20. FF2 is negative 25. Sorry, FA, what are we doing here? FA was positive 50, right? FF1 was neg 20, and FF2 was neg 25. $50 plus neg 20 plus neg 25 gives me 5. 25 times the acceleration equals 5.0. A is equal to 5 over 25, 0.2. Okay, we've just analyzed the external. We just analyzed the system. Okay, we found the acceleration of the entire semi-truck trailer. Now, let's deal with the internal. Let's deal with what's happening inside. Not to the whole thing, but to individual boxes of ice cream on the inside. Let's pick an object. Let's pick object 1. Okay, let's pick object 1 here. It has a mass of 10 kilograms. It has a force of friction of 20 newtons acting to the left. Anything else there? Is there anything else that acts on object 1? Gravity and the normal force, they cancel. I'm going to actually leave those off right now because I don't want to clutter this diagram right now. Is there anything else besides gravity and the normal force? No, not the applied force. No, the applied force doesn't act on object number 1. What am I pulling on? Object 2. Yeah. Object 2 is pulling on object 1. So I pull on object 1 with 50 newtons. Does that cause object number 1 to move forward? Sure it does. Okay, I pull with 50 newtons on object 2. That causes number 1 to pull forward, but not directly because of the 50 newtons, but rather because of this, the force of 2 on 1. In fact, that's what we're trying to find, isn't it? The force of tension in the rope joining the two boxes, the force between the two boxes. Now we're analyzing this object. It's going to be FF plus F21. Hey, why didn't I include the other force? Why didn't I include the 25 newtons? Because it's acting on the other object. When I'm analyzing the whole thing, I need all of them. When I'm analyzing the one object, I look at only the forces that are acting on that one object. M this time is going to be 10 kilograms because I'm only looking at the one. A is 0.20. That's what I just found, right? FF1 is neg 20 plus F21. This is 0.2. Take that over to the other side. Sorry, it's 2, I should say. Take this over to the other side. I get 22 newtons. That's my answer. Let's see if it's reasonable for a second. Okay, I pull on object 2 with a force of 50 newtons. Object 2 has to pull on object 1 to keep it moving, to get it moving, right? How hard does it have to pull? Well, if 50 newtons is required to pull 25 kilograms, then it's going to mean you need less force to pull only 10 kilograms. So that force acting between 1 and 2 is going to be less than 50 newtons. We got 22 newtons there. Let's try this another way. Let's try drawing object number 2. On object number 2, there is a force to the right of 50 newtons. Because we're pulling on the whole system there, right? And that's directly on object 2. There's a force to the left. It's a force of 1 on 2. What do you think we should get here? What do you think we should get here when we solve for F12 here? Force between 1 and 2. What was the other mass? 15 kilograms? Uh, 15 times 0.2 is going to give me, what is that? 15 times 0.2. Oh, wait a sec, missed something. Missed something. Everybody see what my mistake is here? I'm analyzing object 2. William's right. The other force that acts on this is that force of friction. That's going to be the 25 Newton force of friction, FF2. It's acting this way. So we missed one here. It's F12 plus FA plus FF. And that's going to be a negative 25 newtons. All right, let's do it now here. On the left-hand side, we've got 0.2 times 15. That's going to give me 3. Okay, 3 newtons on the left side, 25 on the right side. Take that over by subtracting. It becomes F12 is negative 22 newtons. Is that the answer you'd expect to get? Sure. It should be the same value, right? The force of 1 on 2 is equal and opposite to the force of 2 on 1. That makes sense? So what do you got to do? You got to analyze the external. Okay, the forces that are acting on the trailer, the forces that are acting on the outside, on the entire system. Get whatever you can find. Doesn't matter what it is. Get whatever you can find. Then analyze the internal. Okay, pick an object. Okay, in this case, it didn't matter whether I picked object 1 or object 2. I got the same answer. That's always going to be the case. Pick one. Go with it. Get what you're looking for. Okay? I'm going to leave you here with one question now. Looks the same almost. We want to find the tension in the rope joining these two boxes. In other words, we want to find this force right here. That acts right here. Remember to break it down into two sections. The whole system, and then inside the system, the external and the internal. Let's see what we can get there, okay? Let's have a look at this now. Let's look at the outside of it, the external. Let's look at the internal here. My external says the net force is equal to all of the forces that act on this entire system. That's going to be FF1 plus FF2 plus FA. That's going to be M times A is equal to FF1 plus FF2 plus FA. Total mass here is 20 kilograms. Let's get the acceleration. FF1 is negative 18, FF2 is negative 12, and FA is positive 45. So what do we get there? It's going to give me 15. 15 divided by 20 is 0.75. Is that right? So my acceleration is 0.75 meters per second squared. All right, good. I've done the external. That whole system and everything inside that system accelerates at 0.75 meters per second squared. The back of the semi-truck and all the ice cream within the semi-truck accelerates at 0.75. Now let's look at the internal. Let's pick an object. It doesn't matter whether it's the 12 or the 8. Okay, I'm going to pick the 12. On the 12 kilogram object, there is a force of friction. We're calling that FF1. It's 18 newtons. FF2 doesn't act directly on the 12. It acts on the 8. The 45 doesn't act directly on the 12. It acts on the 8. There's one more force, though, that does, and that's going to be the force of 2 on 1, the force of the 8 pulling the 12. We don't know what its value is, though. Did anybody do this, by the way, by analyzing the 8 kilogram object? Okay. The mass that I'm going to use is 12. The mass that you would have used would have been 8. Okay, the acceleration for both of us, whether you use the 12 or the 8, is 0.75. Negative 18 plus F21. Okay, that's 0.759. Take that over 27, I think it is. I'm going to do a lightning fast calculation in my head and say that Luis and Joe would have gotten negative 27 newtons. Is that what you guys got? Okay. They did object 8, or the 8 kilogram object, and of course the force that's pulling that one between 1 and 2 is going to be to the left. But it's going to be the same value because of Newton's third law. Object A applies a force on B, B applies an equal and opposite force on A. You good? All right. Good news. It's 3:25. There's not time to give you more questions, and you have a nice long weekend coming up that's homework free.